This microcredential deals with identifying types and characteristics of soils and soil components and consists of 5 targeted skills. This targeted skill addresses soil chemistry. Soil activity is not limited to transporting water and other nutrients. It also captures nutrients and ions and is home for important chemical activity involving pH, carbon content, and nitrogen level in the soil. Soil pH refers to how acidic or alkaline the soil is. A pH less than 7 is acidic, a pH of 7 is neutral, and a pH greater than 7 is alkaline or basic. pH is an important measure since it controls the availability of various nutrients needed for plant growth. An alkaline soil has less iron available for plant growth. Most soils have a pH range from 4 to 10. Some plants require an acidic soil with a pH from 4.5 to 6. These plants include azaleas, blueberries, and hydrangeas. If their soil is too alkaline, they cannot absorb nutrients and will become iron deficient and produce poor or no flowers or fruit. Other plants, such as lavender and honeysuckles, require alkaline soils. Since soil usually contains a good amount of organic material, carbon and carbon compounds are the main components of topsoil. With more organic carbon, soil is better aerated, more productive, and stable. Soil is involved in the carbon cycle due to the action of microbes that break down organic material. The natural movement of carbon from bedrock to the soil to the ocean and atmosphere can take millions of years. Soil is oxidized by microbes such as bacteria and fungi, plus invertebrates like some insects and worms that live underground and move through soil and release carbon into the air. Human activity accelerates the carbon cycle when fossil fuels such as oil, gas, and coal are burned, thus releasing carbon into the air. Nitrogen is an important building block for amino acids and proteins for organisms. It is also a main component of plant fertilizer that is added when soil is found to be deficient in it. One natural mechanism for putting nitrogen into soil is a lightning strike that drives atmospheric nitrogen into the soil. Another natural mechanism is the breakdown of bedrock that releases elements into the soil. Higher levels of organic matter enable better soil nitrogen retention, greater microbial biodiversity, and promote the presence and growth of mycorrhizal fungi. These fungi grow among roots and assist with the movement of soil nutrients into plants. When antibiotics end up in groundwater, they infiltrate the soil and diminish microorganisms critical to the nitrogen cycle. Since atmospheric nitrogen, symbolized as N2, is not useful to plants, soil microbes, such as nitrogen-fixing bacteria, fix nitrogen by converting it to ammonia and other nitrogenous compounds that plants can use. Legumes are examples of plants that have nitrogen-fixing bacteria in nodules around their roots. These bacteria convert nitrogen gas into usable nitrogen compounds for plants. Beans, peas, and peanuts are examples of legumes. Nitrogen fixation occurs in nodules that form on plant roots to form a beneficial partnership between the bacteria and the plant. The soil's ratio of carbon to nitrogen is an important balance. Organic material in soil and mulch has a higher level of carbon than nitrogen. But as microbes decompose organic matter, such as a new coat of mulch, the carbon decreases, which in turn increases the proportion of nitrogen, thus making it more available to plants. In closing, this microcredential was an overview of the 3 chemical processes essential to healthy plant growth. They were soil pH and the 2 natural cycles of carbon and nitrogen.